Hello students, in circle lesson inside the alternative statement for this theorem, that is angle between the tangent and secant, that was left by me. So today I will continue this and then we will take two more solved example and then what happens next part we will see. So first of all, what is the theorem of angle between the tangent and secant? So inside it we had seen that if an angle has a vertex on the circle, if an angle has its vertex on the circle, if you see here in this three figure inside, B is the point and it is a vertex of an angle and that vertex is on the circle. Next statement is its one side touches the circle. If you notice here, BC is there. It is the one of the angle of a one of the arm of a angle and it is touches the circle at this point. So B is the vertex. If you see here, B is the vertex in any figure and BC is there, it touches the circle. Okay. Next point what they told you, and other intersect the circle in one more point, and this is the another arm of a circle, arm of a angle. This is another arm of a angle. It, what they told you, intersect the circle. This is intersect the circle. Okay, and one is touches the circle. So BC touches the circle and AB intersect the circle at what, another point, and B is the one of the what, it is the vertex and it is one of the point on the circle. If such a situation is there, then what we have to show that in this statement, in the theorem of tangent and secant, so we have to show that then the measure of angle is half the measure of intercepted arc. So we have to show here, and ABC, angle ABC, anywhere this angle ABC is half of arc ADB, half of arc ADB, and this already I taught you how to prove this. There are three conditions I told you. When there is a what, the arm, one of the arm of a circle passing through the center of the circle, one of the arm of means center of the circle is exterior of the angle and center of the circle is interior of the angle. So these three conditions we had seen that, and what we have to here from this we prove that angle ABC is in any condition this angle ABC, a measure of angle ABC is half the measure of arc ADC, half the measure of arc ADC, that we have proved. But it's a alternative statement I forgot to, means this part I get forgot. So alternative statement for above statement. In above statement inside or theorem inside, what we had seen, this angle ABC is there, it is half of ADB, is half of ADB. This alternative statement we have to study. So here in the its alternative statement we will see now. Alternative statement of above theorem. In figure, AB is a secant. In figure, here figure they provide us, and AB is a secant. If you see here, this is AB and it is the secant, and BC is a tangent. Okay, secant, it intersects the circle in 2 points, and tangent, it touches the circle in 1 point. The arc ADB, where is arc ADB? Here is arc ADB. This is arc ADB. If you see here, you will notice that this is arc ADB. Okay, and is intercepted by angle ABC. If you see here, this arc ADB, it get intercepted by whom? Angle ABC. It is intercepted by this angle ABC. Chord AB divide the circle in two parts. Okay, now this chord AB is there. This chord AB, this is the chord AB, divide the circle in two parts. This is the one part and this is the another part. Okay, it divides the circle in two parts. These are opposite arcs of each other. Okay, and these are there. So ADB, this is ADB and this is ATB. These are the two arcs of a circle and they are opposite to each other. Now take a point T on arc opposite to ADC. So we have to take this point T here. This is point T and on the arc opposite to the ADB. And from above theorem means whatever is there upside. From this theorem, if the one of the arm of an angle is what? Exterior, interior and the on the circle. In any condition, this angle ABC is half the arc ADB, half the arc ADB, that we knows, and that we have to use that. So here what from above statement what we say that this angle ABC is there. Okay, from above statement this angle ABC is half of arc ADB. Okay, half of arc ADB. Okay, and now this is from above theorem we had seen that. Now if we see this angle ABC is what we said, then half of the arc ADC, and same this ATD, if we are taking this angle, this center of the circle is interior of the circle, and so it also intercept ADB. So what we said that this here we can write in this way, angle ABC, here we write it here, angle ABC is equals to 1/2 arc ADC, and same if we are taking this arc angle, then here also what happens, as you know that ATC is half of this what arc, because it is a inscribed angle, and that is angle ATB is equal to also 1/2 arc ADC. Okay, that we already studied, that we have already studied. So from this what we are understanding, if this is the angle and it inscribed this arc, it is also half of the arc inscribed by it, and this angle ABC is also half. So from this what we are saying, suppose this is our first statement, suppose this is our first statement, this is the first one and this is the second one. From this statement RHS is seen, so ABC is equal to ATB. So here we are getting ABC is equals to ATB is equals to 1/2 measure of arc ADB. Okay, and the meaning of it is that means this arc ABC and ATB are congruent to each other, this and that arc. So from this proof we will write the statement for the theorem, and the statement is so what is the statement for this? Angle between a tangent, and this is the angle between a tangent, this BC is a tangent of a circle, and chord drawn from the point of contact, and from this point of contact, which is the point of contact is here B, from B if we draw the chord, so AB is a chord, BC is a tangent, AB is a chord, then what they told you here point of contact is congruent to the angle inscribed in the opposite to the arc intercepted by the angle. So that is our statement. The angle between the tangent means this angle ABC, tangent of a circle and chord. So AB is a chord, BC is a tangent. So angle inscribed by this chord and tangent is angle ABC. This angle ABC is congruent to, okay, is congruent to what they told you, angle inscribed in the arc, angle inscribed in the arc opposite to the intercepted. So this is the angle ATB. This angle ATB is, this is angle ATB, and in that angle inscribes what they told you, inscribed in the arc opposite to the arc intercepted by the angle. So which angle get intercepted by this angle ATB? That is it ADB, it get intercept, and it is located in the opposite arc. So this ADB's opposite arc is ATB, and this angle is also congruent to, this angle is also congruent to, means ATB is congruent to ABC, that we have to prove. That is the statement. It is the alternative statement for the what? Tangent secant theorem. So the angle between a tangent of a circle and chord drawn from the point of contact is congruent to the angle inscribed in arc opposite to the arc intercepted by the angle. So that is the statement. And in short what we say that if ABC, this angle ABC is congruent to angle ATB, and that is the alternative statement for the theorem. Now this part also converse of theorem of angle between tangent and secant, and this part is not for us proof is not there for us, only we will understand the statement of his statement of it. So what is converse theorem of the angle between tangent and secant? The converse of theorem of angle between tangent and secant. So first of all, what is the theorem? Just now we seen that if PQR is there, this PQR is there, it is half of PSQ. PQR is half of PSQ. So it's a line. Converse we will study first. So converse, before converse, what is statement here? What is there? What we proved here? Angle ABC is half of ADB. Okay, this angle ABC is half of ADB. That is the tangent secant, according to tangent secant theorem. So here what they gave us, a line drawn from one end point of chord. A line drawn from one end point. Suppose PQ is a chord. PQ is a chord. Here only given PQ is a chord, and its one of the end point is and its one of the end point is Q. One of the end point is Q. A line drawn from one end point of chord, that is Q is the end point, and from that end point if we draw the line, and TR is a line, okay, chord of a circle, and if angle between the chord and the line, means this is the chord and this is a line, TR is a line and PQ is a chord, and angle between them is PQR, otherwise PTQ, okay, PQR or PTQ, any two angles are formed, and that's why we took here both PQR and PTQ. Is half the measure of arc. Half means PQR is half of PSQ, here given PQR is half of PSQ, and PQT is half of PUQ. PQT is half of PUQ. If such a situation is there, what they told you, if such a situation is there, then the arc intercepted by the angle and then line angle, then this line is a tangent, means TR is a tangent. TR is a tangent. That is the converse theorem of angle between tangent and secant. Okay, so first of all, again we will understand the statement here. What they gave you, if this is a line drawn from the end point of chord, this is the chord of a circle, Q is the end point of the circle, and from this end point if you draw the line here TR, and if angle PQR is half of PSQ, PQR is half of measure of arc PSQ, and PQT is half of measure of PUQ. PQT is half the measure of PUQ, then TR is a tangent. Then TR is a tangent. Okay, so that is our what converse of theorem of angle between the secant. So you have to keep in your mind that if this is the chord and this angle is there, PQR is half of PSQ and PQT is half of PUQ, then TR is a tangent of the circle. Okay, that is the converse. And after that we had studied this point, that is theorem of internal division of chords. That theorem of internal division, inside what I told you, when these two chords are intersect each other internally inside the circle, then PE into EB, AE into EB is equal to CE into ED. Okay, then we see the when this chord intersect each other, what externally to the circle, external to the circle, then AE into EB is equal to CE into DE. That we had seen. Afterwards we seen this also, when tangent and secant inside here, if it is a AB is a secant and ET is a tangent, okay, and if such a situation is there, then ET square is equals to EB into EA, EB into EA, and we seen two solved examples from this, and the next solved example is there that we will see now. So here it is in figure, two circles intersect each other at point X and Y. So here it is, this is the circle, this is the circle, and this is another circle. They intersect each other at 2 points, and which are those 2 points? These points are, this point is X and this point is Y, I shown with the blue color. Okay, then tangent from a point M, then tangent drawn from this point M on line xy. So this is point M, and from this point M, if we draw a line passing from xy, touch the circle, and another tangent if we draw, this is the passing line, and this PMQ and PM, these are the two tangents, they are touching the circles at point P and at point Q. Then we have to show that PM is equals to MQ. PM is equals to MQ. Okay, one more time we will understand. Two circles intersect each other at point X and Y. Then tangent line from the point M. Suppose from this point XY line, from this point line XY, there we have, if we take one point M, and we draw the tangents to the circle from both sides, then PM is equal to MQ, that we have to prove. So fill in the blanks and write the proof. It is there. So actually in a textbook it is a activity. It is a activity. So first of all we'll see here, fill in the blanks and write the proof. MX is a common dash for MX. Where is MX? There is MX is a common. What is it? MX is a common. It is a dash of a circle. It is a common chord of a circle. Which two circles are there? That is for this both the circle. Name is not given. Center of the circle is not given for this common secant. It is chord also and it is secant also. So we will use here common secant for the circle. We have to use tangent secant theorem. So here we have to write it is a common secant for this circles. So if it is a common common secant, then as we know that PM is equal to, just now we seen it here, which this theorem inside, it square is equal to EA into EB, that we have to write here. So I will write here first of all. Here is our figure. Okay, it is common secant, we have to write here. It is common secant. So PM square is equal to what will come here? My. This is My into Mx. Okay, My into Mx. Similarly, if it is, just now we seen the theorem of tangent and secant, and inside what we proved that if it is a tangent and it is a secant, then PM square is equals to what? Mx into My. Okay, Mx into My. So we have to write here, we already written here, this is Mx into My. Similarly, for this triangle circle also, this is secant, xy is a secant and this is the tangent. So here what will come? MQ square is equals to My into Mx. So we have to write here in this way. So here it is secant and here similarly MQ square is equals to, here it will come MQ square is equal to Mx My into Mx, and the reason is tangent secant theorem. If you see here MyMx, LHS is same, so RHS is also same. So what we get it here? QM square is equal to PM square. Okay, PM square and PM, and taking square root, PM is equals to MQ. We will prove. Okay, so I will write here again, you will understand it then. So here it is secant, SECANT. Here PQ square is equals to My into Mx. Okay, from 1 and 2, here PM square is equal to QM square, because RHS is same, and if RHS is same, PM square is equal to QM square, and by taking square, QM is equal to PM, and that we can prove easily. And if it is equal, it is congruent to each other. Understood all of you? Okay, so that is our example. And the next, it is the what? It is the fourth example, and that example inside we have to write proof for this. So this example I am going to explain you, and by using these steps, which steps? These steps you have to solve this example and send me. Okay, so I will explain you the question. If PQ is a diameter, if PQ is a diameter, if you see it is passing from the center of the circle, so it is a diameter and center is O. R is any point on the circle. This is R and it is any point on the circle. Then, and one more thing they told you, that is RS is perpendicular on PO. RS is perpendicular on, sorry, PO, not PQ. So here it is PQ. Then prove that SR is the geometric mean. If SR is a geometric means what? SR square is equal to PS into SQ. PS into SQ, that we have to prove. And for that, what we have to use? These steps, that is draw ray RS. We have to draw the ray RS. Here it is drawn already. RT is the ray. Okay, intersect at point T. So we have to show that RS is equal to TS. If you show this RS is equal to TS, then what happens? You will get the what? If you show this, then next what we have to use here? Write the result of the theorem. Write the result of the theorem of intersection of chords inside the circle. Okay, this RS is equal to TS if you will show, and afterwards what we have to show, that we have to use the property which we use it here, where they intersect in each other internally. This we have to use here, this point, this theorem we have to use, and after that you will get whatever your proof is there, you will get it easily. Okay, so today you have to solve this and send me. If you have doubt, then I will explain you this question in our next lecture. Okay, thank you. So it is very easy. So first this is the main, and that you have to do. If you do this perfectly, if you are capable to show RS is equal to TS, then you will solve this example very easily. So today we will stop here only. Okay, thank you. Have a good day.